Didn't work. No, not. Okay. Okay. This. So I want to talk about first somehow a general definition of what could be entropy and any measurable space. I think that this is not so surprising, really, but for some reason it's not written this way anyway, so I wanted to write it for this conference. And then I will present like at least a setting in which these generalized differential entropies, if you want, satisfy a chain rule. So in the framework of this presentation, we will consider like a general measurable space that comes with some notion of volume attached to it. Okay, so in the most well-known example, the set is just a countable set. The sigma algebra are just all the subsets, and the measure is the counting measure. So this will be the classical Shannon theorem. So you could also take the Euclidean space with the Lebesgue measure. So this will give the usual differential entropy. But with the same reasoning, you could take a locally compact topological group with the, for example, the left Haar measure, and this will also give results that are essentially the same. And well, there is also this framework of taking as a reference measure a probability measure. Okay, so this is relevance in Bayesian inference, for example. And now differential entropy, well, is what one expects it to be, is the expectation of minus the logarithm of the Radon-Nikodym derivative with respect to the volume measure. So it just has this like usual formula with respect to the density. And it's justified on one hand by its probabilistic interpretation. So you have this notion of typicality. If you repeat an experiment independently with certain low rho, you can define a set of typical realizations that it's here and like such that the joint density is close to the exponential of minus n times the entropy. And this set concentrates asymptotically most of the probability. So for any epsilon, you will find some n such that from that, this set will concentrate most of the probability. And moreover, one gets like estimates on the volume of this set that are like a function of the entropy itself. So maybe I will write this in a different way. So the volume, you take the logarithm, you normalize by n, and then you take delta going to 0, because these inequalities also have a delta, like it's the delta used there in the definition. You find the entropy. So in other words, and this is like the vague words but the important ones, the volume of the typical set is something like the exponential of n times the entropy, and the density is approximately constant on this set, and is approximately the exponential of minus n times the entropy. And this is precisely how Shannon introduces this. This is the first coding theorem. And so there is this typical objection here is that the entropy is not invariant. So it would be a bad information measure because it's not invariant under, for example, automorphisms of Rn. But I think this is not a defect. It's just a feature. It's just what we are doing here. I mean, so if you take Rn with a Lebesgue measure and you consider certain automorphism, then the volume of whatever you map under this automorphism is going to change with the determinant. And the entropy, of course, yeah, it's not invariant. There is this term log that A that's going to appear, but this term precisely expresses the fact that the volume of the typical set of the image measure is the image of the typical set. That's the volume of the image of the typical set of the original measure. So there is a mu n here missing. And of course, this has to make appear determinant. Otherwise, the estimates would not work. So this is the same. I mean, for the Haar measures, you will have like a similar thing with the modular function. And another thing that is interesting from the combinatorial perspective is that like these inequalities for the entropy also have a reason. And so the fact that, for example, if you're in the discrete case, the typical set cannot have less than 1 point. So it will have at least measure 1. So this means that the entropy is positive because the entropy is the log of the volume. But in the continuous case, the typical set can have a volume going to 0, so the entropy will diverge to -infinity. So somehow there is no way around this. The entropy has to diverge to -infinity. And then the positivity of the divergence is like another bound. So here is the fact that the typical set has at least 1 point, but the divergence is the opposite of the entropy. And if you take as a reference measure of probability, you know that the size of the typical set won't be more than 1 by definition of a probability. So this gives like the positivity of the divergence. So it's like both can be deduced from these bounds on the typical set. Okay, yeah, this was just a remark. Just one can introduce then this generalized notion of differential entropy. And there is a probabilistic interpretation for it. So now the question is, what can we say on the algebraic side? So are there nice algebraic properties of this generalized differential entropy? Of course, the first that comes to mind is the chain rule. So maybe, sorry, maybe can I take this? It's the chain rule. So there is a problem with the chain rule. So the chain rule is you have to consider the entropy of the conditional measures if you have in mind the discrete case. But if you consider the Kolmogorov definition of a conditional probability, you don't have measures. You just have like functions. So you have to place yourself in a slightly more restrictive case. And well, the framework that I think is good is the framework of disintegrations. So if you have a map between measurable sets, a disintegration is a way of getting a collection of measures concentrated on the level sets of your map, and such that the original measure can be written as an iterated integral. When you integrate a function, you can make this iterated integral. So you integrate first on these measures on the level sets of the map T that we are considering, and then you integrate with respect to certain reference measure that you have in the codomain. So the typical examples of, well, and of course, this gives a regular version of a conditional probability in the sense of Kolmogorov. Well, I said, of course, I mean, you have to compute something. And so the first example of this integration is for finite sets. So this is completely trivial. It's just that instead of making a sum on this set, you can sum on this set and then sum on the fibers. So this is the decomposition of the counting measure, if you want. And then there is another kind of trivial example, not really, it's a theorem too, it's Fubini's theorem, but if you have a product of two measurable spaces that are sigma finite, and you consider the projection on one of these factors, so this is your map T, now you can disintegrate the product measure on the product space as a measure on the projection, so this is the sigma, the factor on which you are projecting, and then you have these measures on the fibers that are just like the injections to the image of the other measure under the injection. So this is Fubini's theorem. So this is a disintegration of reference measure, let's say. And now, if you have a disintegration of the reference measures, so I show this too, then you can also disintegrate any probability measure that is absolutely continuous with respect to that reference measure. So this is the example that we can have in mind. Here, for example, think about this. So here the map T is a projection on one of these factors. So this could be R2, that is the product of R and R. So you project on one of the factors, so the factor comes with its own Lebesgue measure, if you want. So you have a reference measure on the original space, so this would be the Lebesgue measure on the plane. Then you have a map, in this the projection, let's say, and you have a reference measure on the codomain. That could be another Lebesgue measure. And then you have already a disintegration of the reference measures. Then I'm saying that any probability has also this integration that has exactly the same density, but now with respect to these disintegrated reference measures. Of course, this rho t with a tilde don't need to be a probability, but you can normalize them. And if you normalize them, then you have this integration in probabilities, but now with respect to the image measure. So this means that if you want to integrate with respect to rho, you can integrate first with respect to rho t, and then with respect to t star rho. And moreover, like this t star rho has a density that can be computed as the integral of the original density on the fiber. So the integral of R over nu t. And there are some examples. So for example, in the discrete case, this integrating business is just the theorem of total probabilities. If you want to compute the probability of an event, you can compute the probability on the level sets, and then the probability of each possible value. And then this is this iterated integral. Oh, okay. Genial. Allez. Qu'est-ce qu'on fait? Ah, mais c'était déjà là? Non. Ah non, mais ça marche pas. Attends. Je sais pas qu'est-ce qui se passe. Ah. Ne peut pas être ouvert. Ah non, 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 non. Non, c'est pas ça. C'est lui un problème avec la clé. Oui, je pense que je vais copier. Coller. Ouvrir. Ah non, mais désolé.
Pablo, copy your file.
No, yeah, I just did this, yeah. Yeah. Oui, c'est là. OK, d'accord, affichage, mode lecteur, mode plein écran. OK. Ah, OK, désolé, maintenant, on est en retard. Comment faire? OK. Bref. OK, c'est pareil. Dans les cas d'un produit, justement, la seule chose que... Comment?
English.
Ah, sorry. So in the case of a product, the only thing that you get is like, you write this as an iterated integral, and then you renormalize the density. So you get this density, the density of the marginal, and the density on the fiber that is, again, a probability density. So in certain sense, these cases are well known and well understood, but of course, we can try to go further to apply this to cases that are not so well understood. So this is what I want to show at the end. So the observation now is like, if you have a disintegration, then you have a chain rule. So you take a measurable map, and you start with a reference measure here that I call mu, a reference measure here that I call nu. And now we suppose that we have this integration of the reference measures. And so this means that any probability will also be disintegrated. And more than that, we know explicitly how to compute the density of these disintegrated probabilities. So the formula is there. So we have a chain rule. So the entropy of rho with respect to the measure here is the entropy of the image with respect to the measure here. And then we have these conditional terms that have the disintegrated reference measure and the disintegrated probability. What's the proof? Well, it's kind of easy if you know already the previous theorem that I showed. So it's just that if you want to compute the entropy of rho, so you compute the expected value of this, but then it's just algebra. No? So here you normalize by this integral and you multiply by this integral, so comes with this factor, and you identify this as the density of the image probability, and this as the density of the disintegrated probabilities. So it's the theorem that we just saw. So a very easy example that one can start considering is this. So we start with the plane, with the Lebesgue measure that we call lambda. And you project it to 0 infinity, taking the module of the vector. So in this case, so this is the radius, and the change of variable formulas that we use to integrate in polar coordinates is exactly the disintegration of the Lebesgue measure with respect to the Lebesgue measure on this integral too. So you can compute the integral on the plane as an integral on 0 infinity, and then these integrals that are integrals on the level sets, so on the circles of radius r, with respect to this measure here, that is the measure that assignates to this thing, well, what you expect, let's say. and now, if rho has a density f, it has a disintegration, but here you have to pay attention. So the density of the disintegrated probabilities is f, but divided by the integral of f with respect to the lambda r, and the lambda r is r, the theta. And if you take things in this way, if you consider this as the density of the disintegrated probabilities, then you get an exact chain rule. So it's the entropy of the original one can be computed as the entropy of the image one, and then these conditional terms. So this conditional term. But if you go to the literature, normally they add a term here. There is of the type expectation of log r. And they do this because they don't put this r here. So they don't start with like good measures that are in good relation. So I think that, well, it's just a way of writing simple formulas in certain case. So this formula in particular was known. But then there is also a combinatorial interpretation for this conditional term. But well, I don't have much time, so maybe I can come back to this in the question if you want. And what are the Lie? Yeah, so in a particular case of this is obtained for the case of Lie groups. So you start with a Lie group G with a left invariant half measure. And now you have this Weiss formula that says that if you have G, a closed normal subgroup H.
It's not a Weil, it's Weil. It's a German guy.
No, Weil is with a Greek I. A Weil is a French guy. I think you will start a fight here. Like. He's not Hermann Weil, he's André Weil. No, it's not Hermann. Yeah, so you have G, you have H, this is a closed normal group. And so if you have, and then you, of course you will have the quotient, and if you have Haar measures on two of them, then you will have a Haar measure on the third, and you will have this disintegration formula. So you can compute on G, computing an integral on the quotient, and then an integral on the fibers. And these three measures are said to be in canonical relations. So if we go in retrospective, we always need measures in canonical relations if we want an exact chain rule. And so since we have this disintegration, a corollary of what it just show is like you also have like this exact chain rule for in the Haar case somehow. And I think this is known in the literature, but if somebody has a counterexample can show me, but I think in the literature, like there are some cases with groups, but not, they don't consider the chain rule in this general quotient case. But well, we can discuss about this. And so what did I show? I'm almost finishing. So there is a notion of differential entropy for any measured space. The entropy always depends on a choice of reference volume, also in the discrete case. Because you can change, you're not forced to consider the counting measure, in fact. And if you change the counting measure, you are going to change the entropy. So several inequalities have a volumetric interpretation. So this was just a remark, but I think this can be pushed much further. And well, a disintegration or regularization of conditional probabilities that gives you in particular a chain rule. And I have 10 seconds. So in the 10 seconds is like, just to say that the example that I show with the polar coordinates is a particular case of a more general thing. So this is called Poirier formula. So that if you have like a rectifiable set and you project it to a lower dimension, you can disintegrate the integration on this rectifiable set with respect to the Hausdorff measure, with respect to the Hausdorff measures on the level set. So this is this complicated formula here, but it's exactly in the case of polar coordinates what we saw. So also for this case, coming from geometric measure theory, you would have something like a chain rule. And this has also been discussed recently in the literature, but again, they consider like a deformed version of the chain rule where you get the expectation of the logarithm of this Jacobian. So it's like I'm advocating to just see all this as the same thing and maybe choosing correctly the reference measures so that everything is nice. Well, thank you. There are no questions, really.
Send us your email, Caltech, as soon as you are.
Well, yeah, but also the